In the late months of 2025, the Sun launched three enormous bursts of plasma into the void, coronal mass ejections, each containing billions of tons of magnetized particles hurled outward at thousands of kilometers per second. A small interstellar object only a few kilometers wide, known to astronomers as 3IATLAS. It should have been vaporized, or at least shoved off course. Every physical model said that much energy, directed toward a fragile body of ice and dust, would leave a scar, a deflection, some visible wound. But when the smoke cleared, the object had not moved at all. Its orbit was unchanged. Its brightness remained steady. The sun had fired directly at it, and it had simply continued on, silent and indifferent, as though the storm had never happened. That single fact broke the rhythm of our understanding. It meant one of two things. Either the physics we depend on to describe the solar system had failed, or 3IATLAS was not what we thought it was. It began, like so many cosmic stories, with a smudge of light. On July 1, 2025, the Atlas telescope in Chile recorded a faint object moving slowly across the star field. Within hours, follow-up observations revealed something uncanny about its path. The orbit was not an ellipse. There was no return curve, no closed loop. It was hyperbolic, a trajectory belonging to something not bound by the sun's gravity. That made it interstellar, a wanderer from another system, traveling at nearly 60 kilometers per second relative to the sun. For context, that is fast enough to cross the distance from Earth to the Moon in less than 2 hours. At that speed, nothing the sun could throw should leave it unchanged. And yet, that was what would happen. At first, the discovery caused excitement, not alarm. It was the third interstellar object ever confirmed, following the enigmatic Oumuamua in 2017 and Borisov in 2019. Each visitor had rewritten a chapter of astronomy. Oumuamua, shaped like a slab of metal or a fragment of something artificial, had accelerated in ways no one could fully explain. Borisov, by contrast, had behaved like a normal comet, venting water and dust as it curved around the sun. Now came Atlas, larger, brighter, and apparently older than both. By late July, the Hubble Space Telescope and the James Webb Observatory were watching together. Their spectra showed something no comet from our system had ever displayed. A coma dominated by carbon dioxide, almost no water vapor. That meant its surface had been baked and stripped of volatiles long ago, leaving only heavier molecules that required far higher temperatures to sublimate. It was, in every sense, an ancient traveler, possibly billions of years old, forged in a stellar nursery that died before our sun was born. In October, it made its closest approach to the sun, about 1 1/3 astronomical units, just inside the orbit of Mars. At that distance, the sunlight should have boiled the surface gases, brightening its tail, but nothing extraordinary happened until the solar eruptions began. 3 massive coronal mass ejections erupted from active regions on the far side of the sun, one after another in a span of less than 24 hours. They were not aimed toward Earth, so no warnings went out. But their geometry, when mapped against Atlas's predicted position behind the sun, was chillingly precise. Each wave of plasma raced outward along a path that intersected the object's trajectory. Space weather analysts assumed coincidence, but as the first CME left the corona, followed by the second and the third, someone noticed an anomaly in the magnetic readings, a slight repeating modulation, as though the sun itself were reacting to an unseen presence. Then came silence. For several weeks, the object was hidden behind the sun, invisible to Earth-bound telescopes. When it re-emerged, coronagraph imagery caught it exactly where it was supposed to be. No delay, no wobble, no trace of a collision. 3 solar storms had apparently passed straight through it. The data left researchers grasping for explanations. Some proposed that the CMEs had simply missed. The sun's plasma clouds expand like blossoms, not bullets. Perhaps Atlas had skirted the edges. Others argued the object might be unusually dense, composed of metal rather than ice. But its reflective brightness contradicted that. Metallic surfaces would appear dimmer at that distance. Another theory suggested that the nucleus was surrounded by a vast, diffuse envelope that distributed the CME's momentum across an enormous area, cushioning the impact. None of these ideas survived long under scrutiny. The energy involved was simply too great. something else was happening. Something else was happening. A few plasma physicists began to whisper about electromagnetic coupling. The sun's magnetic field is not a simple shape. It twists, reconnects, and folds back on itself in complex ways. When a conductive body moves through it, electrical currents can form, linking the object and the star in a temporary circuit. If 3IATLAS possessed unusual conductivity, perhaps due to metallic compounds or ionized gases in its coma, it might have drawn magnetic field lines toward itself, creating localized reconnection events. In other words, the sun might have been responding to the object's intrusion, hurling plasma back along those connected lines in an attempt to discharge the tension. If that's what happened, the CMEs were not accidents, they were reactions, and the same connection that triggered them could have shielded Atlas from their physical force, redistributing the energy through magnetic pressure rather than direct momentum. It would be the first time in history we had witnessed an electromagnetic feedback loop between a star and a small body. The implications were staggering. We have long treated comets as passive objects, slaves to gravity and sunlight, but plasma physics hints that they can also be active participants, capable of shaping their environment through electric currents and magnetic fields. In that light, Atlas might not have been a victim of the sun's wrath. It might have been a catalyst. By mid-November, solar observatories recorded lingering disturbances in the magnetic field, localized near the longitudes that had faced the object weeks earlier. Something about that encounter had left the sun unsettled. The patterns echoed again roughly 27 days later, when the same regions rotated back into view, suggesting that the underlying magnetic structures had been twisted or re-energized. Whatever passed between the sun and Atlas had not ended when the object moved on. When the news reached the wider community, the debate fractured into two camps. One insisted it was coincidence, a statistical fluke amplified by online speculation. The other saw the fingerprints of a phenomenon we barely understand. Papers circulated quietly through research groups, proposing terms like magnetospheric resonance object and non-gravitational resilience. None offered proof, but all agreed on one thing: the data didn't fit known physics. If electromagnetic coupling explained the stability, then Atlas's composition had to be extraordinary. A comet made primarily of ice and dust cannot conduct electricity well enough to interact so strongly with solar plasma. That left two possibilities. Either the nucleus contained a significant fraction of conductive material, iron, nickel, carbon chains, or the surrounding coma behaved as a self-organizing plasma, generating currents that shaped magnetic fields on its own. Both scenarios placed the object far outside the category of an ordinary comet. Consider the energy balance. A typical CME carries around 10 trillion kilograms of material, moving at up to 2,000 kilometers per second. The momentum transferred by such a wave, even if spread over seconds, would nudge any small object by measurable degrees. Yet every calculation of Atlas's post-conjunction position matched predictions to within less than 100 kilometers, an accuracy too precise for chance. It didn't just resist the impact, it appeared to ignore it. So the question shifted from what happened to it to what is it? The natural explanations came first. Perhaps it was a fragment of a rocky exoplanet's core, flung into space by a catastrophic collision. Such a shard would be dense enough to shrug off a CME's pressure. And if pockets of carbonates or trapped gases existed inside, heating near the sun could release carbon dioxide, creating the observed coma without water. That would make it a relic of a world destroyed long ago, an alien fossil crossing our system by chance. Another theory traced it back even farther, to the early galaxy. If Atlas formed around a low metallicity star billions of years before the sun, its chemistry would differ profoundly. Its crust might be infused with magnetic minerals created in environments no longer common. Over eons of cosmic radiation, those minerals could become magnetized, giving the body its own residual field. A magnetized nucleus passing through the sun's plasma could plausibly generate the coupling effects we saw. It would be an ancient survivor from a time when the Milky Way itself was young. And then there was the idea that refused to die, the artificial hypothesis. Some researchers dismissed it outright, unwilling to repeat the controversy that followed Oumuamua. Yet the parallels were too obvious to ignore. Anomalous acceleration then, anomalous stability now. If a civilization capable of interstellar engineering wanted to study stars up close, it would build probes designed to endure stellar proximity, to absorb or deflect plasma, to harvest magnetic energy, to ride the storms instead of fleeing them. To human eyes, such a probe would appear comet-like, bright, reflective, venting gases for thermal control, and when the sun attacked, it would remain motionless precisely as Atlas did. No evidence supports that conclusion, but the coincidence tempts imagination, especially because just after perihelion, Atlas brightened briefly, an increase in luminosity lasting less than an hour, then dimmed faster than models predicted. To some, it looked like a burst of activity, to others like a signal. Afterward, the object faded steadily as it receded beyond Mars, its trail thinning until only the largest observatories could still detect it. By the end of December, it was gone, sliding back into the black between the stars. What remains is data, spectra, magnetic readings, solar logs, and a mystery with no resolution. Every explanation seems to raise new questions. If it was natural, why did it behave as if shielded? If electromagnetic, how could such a small body generate current strong enough to affect the sun? And if artificial, where did it come from and what did it learn while it was here? The human mind seeks narrative, cause and effect, but space often refuses to give it. Out there, events unfold on scales that dwarf comprehension, leaving us with only the shadows cast on our instruments. 3IATLAS is one of those shadows, a reminder that our physics is a local dialect spoken in a vast, multilingual universe. What should trouble us most is not the possibility of alien engineering or exotic matter, but the simplicity of our surprise. We assume the sun is the unchallengeable center, the ultimate source of power. Yet in this encounter, it may have been the one tested. 3 times it unleashed its strength, and 3 times the intruder held its course. If that was a coincidence, it is a remarkable one. If it was an interaction, it means stars themselves can be manipulated by phenomena far smaller than we imagined. Far smaller than we imagined. Future telescopes will search for it again as it drifts beyond the heliosphere. In a decade, perhaps the next generation of infrared observatories will pick up its faint reflection, and we'll learn whether it truly kept its speed or altered course once it left the sun's influence. Until then, it remains both an object and an idea, a riddle written in plasma and light. In the end, the story of 3IATLAS is not about fear but perspective. For centuries, we believed comets were omens, harbingers of change. In a sense, they still are. Each interstellar visitor expands the borders of what we think the universe allows. This one simply widened them a little more than most. It came from nowhere, crossed the heart of our solar system, endured the fire of a star, and departed without explanation. It left us wondering whether the sun can truly burn everything that enters its reach, or whether some things carry their own light, untouchable and enduring. If one day we discover that the storm between 3IATLAS and the sun was a conversation, not a battle, we will have to rewrite not just textbooks, but our place in the cosmos, because then we will know that even stars can listen. And somewhere, out beyond the orbit of Neptune, a faint speck of dust and metal is still moving at 60 kilometers per second, unbothered by gravity, indifferent to our curiosity, leaving behind only questions that glow as fiercely as the star it refused to obey.